Hello and welcome once again for another ES340 video. So this is ES340 Day 3, Part A, probably going to be the only part for this. I don't think there's going to be a second video. So what I want to start with is a discussion about total energy, because really where this course is heading is in the direction of energy, and there's going to be two major things that we deal with, and one of them is going to be the total energy, which will be related to the first law of thermodynamics. So the idea, and we've kind of already hit on this a little bit with gravitational energy. So if the only force acting is gravity, as should have been clear from your readings and such last time, then the total change in energy, so we'll call that delta E, has to be equal to zero. This is known as energy conservation if gravitational force is the only force acting, then delta E is equal to zero. And this is a statement of the conservation of energy. Now, if there are other forces acting, of course, delta E can be equal to something else, and that's also a statement of the conservation of energy. But basically, if the only thing that's acting is the gravitational force, then the change in energy has to be zero. And that means that the only way that energy can change forms, if you will, is by going between kinetic energy and potential energy. So it can go back and forth between kinetic and potential energy if the only force is gravity. So now then we need to figure out what delta E, so the question is, what happens if gravity is not the only force? For example, we have a battery, which is an electrical kind of, which is an electrical energy transfer that's happening. Or we can have a paddle wheel, which is a mechanical form of energy transfer happening, right? So then obviously delta E is not going to be equal to zero. It's not equal to zero. And we write it like this: delta E, which can be non-zero, is equal to delta KE plus delta PE. So now we're seeing movement of energy around between kinetic and potential energy, just like before, plus delta U. And those don't necessarily have to cancel each other out, right? Because delta E might not be equal to zero. So this is kind of this is an actual very important equation that we're going to be using a lot. This is called the energy balance equation. And it's going to be used a lot in this course, okay? And because this is really a statement of the first law of thermodynamics, which is that energy is conserved. So even though you can have a change in energy, the change in energy has to come from shuffling around these different forms, right? So this is a statement of that. You can't create energy, you can't, so energy can't be created from nowhere, it can't be destroyed, so it just gets moved around into different forms, basically. Now the delta U, you might be wondering, the PE and the KE is obviously its own form of energy, but this is something that we just call the internal energy change in this case. So we will use U for internal energy throughout the course, and delta U is the internal energy change. Now, there's a lot of different types of energy that kind of just get lumped in here. And if you want to read more about that, you can in your book, because they discuss, they'll discuss all the different ways that that could happen. There's nuclear forces. So if you have like a dense gas, for example, there might be some nuclear forces that are acting on it internally in the system. If we define the system to be a bunch of the gas and things like that, and other forces as well, friction and all of these kinds of things. But we kind of lump that all into internal energy change. So it's really kind of a catch-all for all of these other things that could be happening. So this is going to be very important throughout this course, this equation, the energy balance equation. Now we've discussed work, we've discussed kinetic energy and potential energy, and we've now discussed the total energy, which includes internal energy. But there's another way that energy can be shifted around, and that's through heat. And for this course, for the book, we have a quantity called Q, which is the heat transfer. Now, a lot of times we might just get lazy and use the word heat to mean heat transfer. So I'll probably do that myself when I'm discussing this. But really, this is a heat transfer. And much like this is not a property, much like work. And you can say, well, why is it not a property? So the easiest, perhaps, way of describing something that is a property versus something that isn't, I've discussed it in a variety of ways up to this point, but I think this is another way that is pretty clear. The way that you can tell if something is a property is if I go for state one, I have a state one, and then I have a state two. It makes sense to say I have volume V1 at state one and volume V2 at state two, right? But it doesn't make sense to say I have heat transfer Q1 at state one. Rather, Q1 to 2 between states 1 and 2. Okay, so that's why, hence, Q is not a property. So it makes sense to say I have the system when it's at state one, it has volume one. But it doesn't make sense to say that at state one, I have heat transfer one, right? It makes no sense. What happens is that there is heat transfer that happens between state one and two. So I need to account for both state one and state two in my analysis of heat transfer. The same thing with work. So I need to define at least two states to have heat transfer. I need to define at least two states to have work. Whereas a single state is fine for defining the volume or the mass or things like that, okay? So that's the difference between something that is a property and something that's not a property. Okay, so now we know we have heat transfer, and heat transfer is a method for moving energy around, right? Just like work is another method for moving energy around. We have these two methods now. We have work, which is typically either mechanical or electrical in nature. For this course's purposes, there's other ways that work could be done, but for the most part, we'll be dealing with electrical or mechanical type work. And then there's also heat transfer, which really just comes about because there's some difference in temperature between the system and its environment, okay? So these are the two different ways of transferring energy between states. Now, for the textbook, we have the following sign convention. Q is greater than 0 if there is heat transfer to the system. And Q is less than 0 if heat transfer is from the system. Now this is actually the exact opposite of work, the sign convention for work. And there's a historical reason for that. And probably about half of the textbooks use this notation, which will occasionally, I will occasionally make errors probably there. So if you catch me, please make sure to shout out that I've made an error in the convention, because a lot of times the way that these things get defined, let me just move this. Can I move this down? The way these things get defined is in terms of delta E is equal to Q minus W for this textbook. So basically, by defining W in exactly the opposite way, we have to then introduce a negative sign here to make this to make all the calculations work out. So Q and W in this book are defined opposite each other. Some textbooks use Q plus W, which means that the sign convention is the same for both. So we just have to be careful there. And as I said, if you catch me accidentally flipping that, please do stop me. Okay, so now notice we have this equation, which is the energy balance equation, and we also have this, which says that the change in energy has to have, well, obviously in order for there to be a change in energy, there must have been transfer either to or from the system, right? So delta E can't be 0 in that case if there's no change in energy. Therefore, there must have been some way of moving energy into or out of the system, and generally to or from the environment is how that's done. And so these are the two ways that we can do that, which is either with heat transfer or with work. Okay, so this is going to all swing back around, and we're going to use this in much more detail a bit later in the course. This video, it's not going to be tremendously important in this video, but it will be there. So major ways of having heat transfer. Okay, because now we're dealing with heat here, so we need to figure out the ways that we could transfer heat. Just like up here, we talked about ways that you could do work, right? You can have electrical energy, you can have mechanical forces like a paddle wheel or something like that are happening to give us work. What are the ways that we can have heat transfer? One of them is actually highlighted over here in this figure on the left, which I'll discuss in one moment. But there are a couple of different ways that we can have this. Through conduction, through convection, and through radiation. These are the three major ways. So I can have heat transfer through conduction, which is not like actual physical contact of materials, which is what's shown here on the left. Through convection, which is basically by transfer through having motion of some fluid or something like that, like air. So notice that conduction and convection both require some kind of contact happening. But radiation actually is one that requires no contact whatsoever. And so we're going to discuss all three of these, but basically, the sun radiates energy to us, and it doesn't require a medium, so there doesn't have to be air in between. It can travel through the vacuum of space. So radiation energy is kind of special in that way, and it's really the reason that we even have life on this planet. Okay, now let's talk about through conduction. Okay, so through conduction, we have something like this, which is the heat transfer rate, the rate of heat transfer, which is Q dot. So it's the derivative with respect to time of Q, is equal to negative kappa, which is a fancy looking K, it's a Greek letter, times the area times the derivative of the temperature with respect to the position x, in this case, if we're only looking across one dimension. So we can actually think of temperature as having a profile across space, right? So it can, the temperature, because it's an intensive property, it can have different values at different points in space. And unlike any of the extensive properties that we have, it's not going to have different values in different places. We have to define the whole thing, and then that thing will have a particular mass, right? And it can be broken up into pieces, of course, but you sum up the pieces to get the total mass. In this case, the temperature can be different at different points in space. And we're simplifying things, assuming that we're only going in one direction, which is x, right? To make this simplification. Now, a lot of the times, what we'll do what we'll do is we'll make some kind of simplifying assumption here. And this example on the left gives us a simplifying assumption, basically that if we assume, as shown in the figure, that the temperature changes linearly with respect to x, then we get q dot in the x direction is equal to minus kappa times the area times T2 minus T1 over L, where L is equal to x2 minus x1. Okay? So the idea here, so basically, if it's linear, right, a linear rate of change, the derivative of t with respect to x is going to be constant, right? The derivative of any line is just a constant. In fact, we know what that constant is if we define the line, and that constant is exactly the slope of that line, right? So the derivative of a line is just the slope of the line. Okay? And so this, as you can see, is just the slope, in this case, of the temperature with respect to x. The rise over the run, right? You can see that right here. So that's why it simplifies into this form. And this will be, we'll probably do some example problems using this kind of an equation, right? Now there's another type that I mentioned already, which is through radiation. So this is conduction. And this is known as Fourier's law. We also have radiation. Which is Stefan Boltzmann law. Which gives us that the rate of heat transfer is equal to this little epsilon. Epsilon here is what's called the emissivity, and epsilon has to be between 0 and 1. So it can have perfect emissivity if it's 1, it can have no emissivity if it's 0, and obviously it can take on values in between, times sigma, where sigma is the Stefan Boltzmann constant. And it's given by, in SI units, it is 5.67 times 10 to the negative 8th watts per meter squared times Kelvin to the 4th. And in English units, it is 0.1714 times 10 to the negative 8th BTU per hour times foot squared times degree R to the 4th, where degree R is Rankine. So basically it has the same, Rankine has the same units as Fahrenheit, but it has, it is 0 at absolute 0. So that's, so it's an absolute temperature. And so basically we're gonna have to use absolute temperatures here when we're making these kinds of calculations, which you will see. But anyways, QE dot is equal to epsilon sigma times the area times the temperature of the body to the fourth. Okay, so that will be the heat transfer coming from a body. And if the surroundings can be taken to be much larger than the body, then we can use QE dot is equal to epsilon times sigma times A times T B to the fourth minus TS to the fourth, where this is the temperature of the surroundings. Okay, so if we just want to know how much this is radiating without any respect to its surroundings, we would use the top equation. If we want to, if we can assume that the surroundings are much larger and the surroundings have some well-defined temperature, then we would use this one to calculate the rate of heat transfer. And then, of course, finally, we have convection. And this one is going to use Newton's law of cooling. So basically, then Q dot in the convection type is equal to some value H, which you'll have to find the value of that on some table. Let me just look up what the table is, 2.1 in your textbook. That's the table that we'll be using when we make these kinds of calculations. So you'll find the value of H, which is a constant, but it's relative to a certain variety of situations, times the area, times the temperature of the body, minus the temperature of the surrounding fluid. Usually that'll be air. And then this is obviously the temperature of the body. Okay, so these are the three major ways of getting heat transfer, and you can actually calculate out what the heat transfer rates would be. So each of these is heat transfer rates, right? Derivative with respect to T in this case, not just plain Q. Now you can find the amount of, you can find directly Q by integrating with respect to T, which we may do from time to time. But more often than not, most of the problems that you'll deal with in this book, you're just going to be given Q rather than being forced to calculate it. But we should be prepared to be able to calculate these things. Okay, so now we've just to recapitulate what we've done. We talked about total energy, the total change in energy, the conservation of energy, and we've talked now about heat transfer, which is a major way of transferring energy, much like work was, which we discussed in a previous video. And you should be prepped to do problems involving heat transfer. Okay, that's all that I have for this video, and I hope to see you again soon.